Welcome to a webcast made by the Learning Enhancement team based in the Dean of Students office at the University of East Anglia. This webcast is part of the Steps into Vectors series and concerns basic operations with vectors. This guide gives pictorial and algebraic explanations of how to add and subtract vectors and also how to multiply a vector by a scalar. Introduction. Vectors are a very important idea in all areas of science. For example, much of modern physics relies on vectors and the theory that describes them. A vector can be thought of as describing a journey from one point to another, and in fact the word vector comes from the Latin for passenger or carrier. Importantly, a vector describes a measure which has both a magnitude, a size, and a direction associated with it. In mathematics, something which has a magnitude but not a direction is called a scalar. Vectors and scalars are related but different. Vectors have magnitude and direction. Scalars have only magnitude. The study guide, Basics of Vectors, explains the concept of vectors and scalars in more detail, along with the fundamental language used to describe them. If you are not familiar with vectors, then you should read this guide before proceeding. You should pay particular attention to the description of a vector in terms of the rectangular unit vectors. I. The unit vector, a single step, in the positive x direction. J. The unit vector, a single step, in the positive y direction. K. The unit vector, a single step, in the positive z direction. Describing a vector in this way leads to a simple method for their addition and subtraction. Adding and subtracting vectors. When you add two vectors, you can visualize the process as laying them end to end. For example, if you wish to add vectors A and B, you can think of it as vector B beginning at the end of vector A. A plus B is illustrated to the left. You can also add B and A where the vector A begins at the end of vector B. B plus A is illustrated to the left. By combining both these pictures, you can see that it does not matter which way around you add the vectors, as the journeys they describe begin and end at the same place. They simply take different routes. The vector which describes the overall journey, represented by the addition of vectors, is called the resultant vector. Here, if you call the resultant vector C, you can combine the two diagrams above together and see that B plus A and A plus B both describe the same beginning and end points of a journey. This diagram shows that mathematically A plus B equals B plus A, which equals C. The diagram also shows that if you add the number of steps in the x direction in A and B, you get the same number of steps in the x direction of the resultant C. This is also true for the y direction and also the z direction. By expressing A and B as the general vectors, vector A equals A1i plus A2j plus A3k, and vector B equals B1i plus B2j plus B3k, you can calculate the number of i's, which represent steps in the x direction in the resultant C, by adding A1 and B1, the number of j's, which represent steps in the y direction, by adding A2 and B2, and the number of k's, which represent steps in the z direction, by adding A3 and B3. You can write this mathematically as A plus B equals C, which equals A1 plus B1i plus A2 plus B2j plus A3 plus B3k. Example, given that vector A equals I plus 2j plus 3k, and vector b equals minus 2i plus 6k, what is a plus b? In this question, a1 equals 1, a2 equals 2, a3 equals 3, b1 equals minus 2, b2 equals 0, and b3 equals 6. And so, a plus b equals 1 plus minus 2i plus 2 plus 0j plus 3 plus 6k, which equals minus I plus 2j plus 9k. In other words, the resultant vector from adding a and b is c equals minus I plus 2j plus 9k. Similarly, b plus a equals minus 2 plus 1i plus 0 plus 2j plus 6 plus 3k, which is also minus I plus 2j plus 9k. Subtraction of vectors can be thought of in a similar way. Remember that a vector which has the same magnitude but opposite direction to another vector is the negative of that vector. So here is vector b, and vector minus b is the same length, it has the same magnitude, but points in the opposite direction. If you wish to subtract the vector b from vector a, you can think of adding the vector minus b to a. To the left is a representation of a plus minus b, which equals a minus b, which equals c. Here's vector a. Here's vector minus b, which begins at the end of vector a. And here's the resultant vector c. You can also subtract a from b and show that the resultant is minus c. To the left is a representation of b plus minus a, which equals b minus a, which equals minus c. Here we start with vector b and add minus a, and the result is vector minus c. Again, by expressing a and b as the general vectors, vector a equals a1i plus a2j plus a3k, and vector b equals b1i plus b2j plus b3k, you can write a general formula for subtracting vectors as a minus b equals a1 minus b1i plus a2 minus b2j plus a3 minus b3k. Example, given that a equals I plus 2j plus 3k and b equals minus 2i plus 6k, what is a minus b? Here, a1 equals 1, a2 equals 2, and a3 equals 3, b1 equals minus 2, b2 equals 0, and b3 equals 6. And so, a minus b equals 1 minus minus 2, I, plus 2 minus 0, j, plus 3 minus 6, k, which equals 3, plus 2i, which equals 3i, plus 2j minus 3k. Multiplying a vector and a scalar. You can visualise adding a vector to itself as laying multiples of that vector end to end. As you have seen in the previous section, this also represents addition of vectors. For example, a plus a is shown to the left. The resultant vector is 2a. Similarly, if you add another a, you get a plus a plus a, which has a resultant 3a, and so on. In this way, you can see that successive additions of a represent multiplying the vector by a constant or a scalar. You are not restricted to whole numbers, and for example 0.5a would represent a journey to halfway along a. When you multiply a general vector a equals a1i plus a2j plus a3k by any scalar m, you affect the values of the coefficients of I, j and k, which are a1, a2 and a3. It is important to note that I, j and k are not affected themselves. You can write this mathematically as the scalar m multiplied by a equals a1m I plus a2m j plus a3m k. In other words, you multiply the scalar parts of a by the scalar m. Example, given that vector a equals I plus 2j plus 3k and vector b equals minus 2i plus 6k, what is 1, 2a, 2, minus 3b, 3, 2a minus 3b. 1. Using a1 equals 1, a2 equals 2 and a3 equals 3, 2a equals 1 multiplied by 2, I, plus 2 multiplied by 2, j, plus 3 multiplied by 2, k, which equals 2i plus 4j plus 6k. 2. Using b1 equals minus 2, b2 equals 0, and b3 equals 6, minus 3b equals minus 2 multiplied by minus 3i, plus 0 multiplied by minus 3j, plus 6 multiplied by minus 3k, which equals 6i minus 18k. 3. Using the results from 1 and 2, 2a minus 3b equals 2a plus minus 3b, which equals 2i plus 4j plus 6k plus 6i minus 18k, which equals 8i plus 4j minus 12k. Further guidance and information. If you have any further questions about mathematical skills or would like to discuss any other aspects of mathematics, you can talk to your lecturer or personal advisor or make an appointment to see a learning enhancement tutor in the Dean of Students office. You can telephone 01603 592761, email dos.help@uea.ac.uk, or visit our website at www.uea.ac.uk/dos/let. There are further resources on many other aspects of numeracy, mathematics, statistics and science available from the Dean of Students office and on its website. These include questions to practice, model solutions and webcasts illustrating essential skills. This guidance is one of a series on mathematics produced by the Dean of Students office at the University of East Anglia.